Welcome to Frank Stajano Explains. This is the online version of my lecture course on algorithms at the University of Cambridge, where I am a full professor of security and privacy. COVID-19 has forced us to do many things differently, and I miss lecturing to a live audience where I can ask questions, I can check if people are following what I do, are you still with me when I'm in the middle of something complicated, find out if I should slow down or speed up, or give additional details on a point that I'm not making clear enough. And also, when I'm lecturing to a live audience, to 150 of you, there's an intensity that I kind of miss when I'm just speaking to a camera. So I guess sometimes I will intersperse recordings of actual lectures that I gave in the past. But anyway, since I now, one way or another, I have to produce these lectures online and invest over 100 hours of filming and editing and stuff like that, then I told myself I might as well take advantage of this situation and reach a much broader audience. And that's how I decided to put them up on my YouTube channel for everyone else as well, not just my own Cambridge students. The content I plan to explain on this channel, besides my official lectures, includes other topics that might be of interest to aspiring computer scientists, or to people who want to come to Cambridge, or to people who want to do a PhD in computer science, or to start their own company in the computer field and other related things like that. But for the benefit of my first year Cambridge undergraduate students who are here because you can't meet me in the lecture theatre, I have made for you a playlist that includes just the lectures that cover the material in the syllabus for this year's algorithms course. You don't have to watch any of the other stuff, although you're most welcome to do so. If, on the other hand, you are not a Cambridge student, maybe because you are at some other university, maybe because you are still in high school and you want to see what it would be like to study computer science at Cambridge, or because you want to learn computer science on your own, well, you're most welcome to join us. This is the genuine article, and you will get exactly the same lectures as my Cambridge students. It's all free, you don't have to pay anything to attend. And whether you are my student or not, just click the like button and subscribe if you want to encourage me to continue to publish my content openly on this channel. But to get any value out of these lectures, whether you are officially one of my students at Cambridge or not, you need to invest your own effort and dedication in this course. It's not enough just to grab the popcorn and binge watch 12 hours back to back, because if you do that, it goes in one ear and comes out the other. You must instead actively work on this material, and in particular, you must write your own programs to exercise the ideas we explore in this course. This is really the only way to own this material. You cannot learn to play the piano just by watching someone's piano lectures, even if that someone is the best pianist in the world. To become good, you also have to practice on your own several hours a day. That's the same for computers. Don't try to memorize this stuff. You really want to understand this, and the best way to understand it is to recreate it by yourself and build a program to implement each concept that we study together, and debug the program until it works. This is the path to mastery in this course and in all of computer science in general. Because this is a recorded video, if there's anything you don't quite get on the first time, then you can always go back and rewind, of course. You can also visit the course webpage to grab my lecture notes, which cover the same material. And if you find a mistake in this video or in the handout, then tell me in the comments, and I'll fix it for next time. But if you want to learn this content, and certainly if you are one of my Cambridge students, I recommend that besides the handout, you also get yourself a paper notebook, and you write your own notes explaining in your own words what you got out of each lecture or each video. And articulating your questions about the bits that you didn't quite understand yet, and maybe going back to your notebook after a while and see if you can answer your own questions after you have digested the material a little better. Imagine that you have to explain the content of the video to someone who wasn't there, and in the process of doing so you understand whether you actually got it or whether it's still a bit sketchy. I mean, it seemed like you understood it, but when you try to explain it, then you realize you didn't. If you do that, you will become so much more strong on this material than those who just listen passively. Algorithms and data structures are truly the core of computer science. And by the time you come to university to read computer science, you will have already done some programming, of course, and by the time you take this course, even though it's a first-year course, you will have already taken some other classes that cover programming and involve some algorithms, because obviously you can't do any programming without using algorithms. But algorithms are a foundational topic, not just matter for this course's exam, but for every other course you do in the computer science tripos and everything else you do in your computer science career. So if you're going to get a degree in computer science, it's important that you understand algorithms and data structures in depth, not just superficially. And so this is really one of the courses where you want to complement the lectures and the handout with a solid textbook, such as this one. This is the one I recommend, Introduction to Algorithms by Cormen, Leiserson, Rivest and Stein. Get yourself a copy of this book. Study it thoroughly, write your notes in the margin, and I know that some of you have already studied most of this book even before coming to Cambridge, and well done to you. Every serious computer scientist has a well-thumbed copy of this book on their bookshelf, and there is a reason for that. You want to be part of that club. So what is an algorithm? An algorithm is a systematic recipe to solve a problem. Systematic means that we are very thorough when we describe exactly what happens in every possible case, so that our recipe works even if it's applied mechanically by a machine that is totally devoid of common sense. So if something odd happens, you or me might adjust or fix the recipe. No, the machine won't. And so you have to be very precise. Actually, most programming is quite mundane. The difficulty in getting a program right is handling the complexity and the large scale. But the individual program sections that you write, 90% of the time, are not that hard. They just mostly move data around. But here, in this course, we'll see some core programming gems that are pretty clever, maybe just a couple dozen lines long, but truly ingenious, and you wish you had come up with that kind of stuff. So often these bits of cleverness are so useful and yet so easy to get wrong in subtle ways that they are written and debugged once and for all, and then packaged up for reuse in standard libraries. The point of this course is to study these kinds of core things, even though they already exist in libraries. Many of the fundamental algorithms that we study would indeed be available in some library, and you wouldn't rewrite them yourself. But here we take the viewpoint of the person who starts from zero and builds that library. So you've probably already done some programming, and you might say, oh well, for this particular problem I might use a hash map from the Java collections library. But no, imagine you only have plain memory at your disposal, no pre-packaged hash maps or any other fancy things, array lists, forget about that. And you have to build all your data structures from zero yourself in machine code being the only language that the processor natively understands. Or at the best in C, which is kind of a polite version of machine code, and without relying on libraries written by others. You are not a programmer until you've wrestled with some hairy pointer code, and when you handle recursive data structures with lots of crisscrossing pointers and all that stuff. When you finally remove the last bug from that kind of code and it behaves as it should, then that light bulb moment you get is priceless. I can explain the subtle points of algorithms and data structures to you until I'm blue in the face, but I can't make you a great programmer. For that, you have to contribute by writing and debugging your own programs. So my goal here in speaking to you through these recorded videos, more than teaching you things, is to inspire you to want to stop watching the damn video and instead opening your editor and starting programming the stuff we've been talking about. I plan on giving you many opportunities to do that. I want you to have that light bulb experience for yourself. And once that happens, you will agree with that old programmer saying that programming is the most enjoyable activity you can engage in with your clothes still on. Now, algorithm. When we say a systematic recipe to solve a problem, what kind of problems are we talking about? Well, let me introduce this course by giving you 3 problems. Try solving these 3 problems yourself as seriously as if they were exam questions, and your grades for this course depended on your answers. So think about what algorithm will solve this problem. What data structure should I employ? The lecture course will eventually tell you how to do things, but you will benefit if you have thought of how to do it on your own before you are given a solution. So the first problem is that of DNA sequences. It's a toy problem. Real problems with DNA sequences are much more complicated, but okay, this gives you a flavor for something. You have a string of the letters A, C, G, and T, and these strings can be very long, and given 2 of these strings, you want to find out how similar they are. See if 2 organisms are related or other things like that that geneticists do. So we define what is a subsequence of a sequence. A subsequence is simply the letters of the sequence taken in order with some of them dropped out. 0 or more letters drop off your original sequence. That gives you a subsequence. So I have a few examples up here. Drop a few letters, you get a subsequence. Now, imagine you have 2 such strings, and the degree of similarity between the 2 strings is measured, we define, by the length of the longest subsequence they have in common. Okay, so then you want to find what is the longest common subsequence between these 2 strings. Well, for example, AC is obviously a subsequence of both, but maybe there are longer subsequences, and you can try eyeballing for a longer subsequence, but how can you make sure that you have found the longest possible one? Well, to make sure you don't miss anything, you could try all possible subsequences of the first string, all possible subsequences of the second string, and then compare them pairwise. That will certainly work and find the longest one. But how long will it take? Well, how many subsequences are there for each of these 2 strings? Try and figure that one out and write it in your notebook. How many pairs do they form? And how long will it take me to check each of these pairs? If your inputs, instead of being just 20 characters or so long, are millions of characters long, if you were to run this algorithm on your computer, would it terminate before you take the exam for this course in June? Try and have a little calculation to see how long that would take. So that's our first problem, DNA sequences, or to abstract away from DNA, just the longest common subsequence between 2 strings. Our second problem is what I call bestseller chart. So imagine you have a large online store. Well, these days, one of the largest companies in the world is an online store. And this global online store has a catalog with lots and lots and lots of items, millions and millions of items. And there are lots and lots of transactions that happen all the time, 24 hours a day, lots of transactions per second. And that online store wants to have a web page with the top 100 best-selling items, the 100 items that sold the most. historically, from minus infinity. And it wants to keep refreshing this page every second. So you have an up to the second list of the 100 best-selling items on the store. So a trivial way of doing that would be to take the millions of items and sorting them every second. I mean, every item, of course, is associated with the number of times it has been sold, and you use that as the key for sorting the items. And if you resort them every time you need to present the page, then you certainly give the correct result. You just take the top 100 after sorting. But you are throwing away all the millions that are not in the top 100. Is there perhaps a better way of solving this problem? A better way would be one that takes less time, since you have to repeat that operation once every second. Well, think about that too. The third problem or puzzle I am posing to you is that of database indexing. Database indexing for one of several possible purposes. Let me bring the example of an auction site. Again, a very large internet company that I'm sure you're familiar with is an auction site that has lots and lots of transactions where people bid in order to buy items. And each one of these transactions is certainly recorded somewhere in a database for this auction site. And you could conceivably, within the auction site, want to have some business logic that checks these transactions and wants to walk through the transactions sorted by seller. Or maybe it wants to walk through these transactions sorted by buyer, or maybe sorted by date, or maybe wants to go through them in order by price. And you don't really want to resort all the millions and millions of transactions every time. You might like to go from one of these views to the next view and then back without having to redo the work. So could you conceivably build some data structure to help with that? The indexing would be building an index data structure that lets you access the series of transactions in any of these specified orders. How would you go about building such an index? How would it work? How would it scale when the data structure grows very large? And would it still work if you start having to add more transactions because more bids are placed on items? And would it work if some of these transactions are deleted? That's an even more complicated problem. Maybe not particularly applicable or realistic in the case of the auction, but in general database case, you certainly might have to delete some records. Would the indexing structure that you might have come up with still work in that case? And what do you need to do to ensure that it does? So think about these three problems. And in due course, during one of the future lectures, we will study particularly good and ingenious ways of addressing them. So to address these and other problems, we want a specific recipe and often also a specific data structure to solve the problem. But how do we convince ourselves that the recipe we produced is correct? Can we prove that our algorithm works in every case? It's not enough just to have something that seems to work in generic instance. It has to work in every case. And how long does it take to run? How long does it take to run? Usually, how long does it take to run? If I'm lucky, how long does it take to run in the worst possible case? Because I want to make sure that it's not going to be exceeding my resources. What other resources does it use up besides the time it takes to run? Maybe how much memory it uses, maybe some other things. Can you think of other resources that a running program might be using? And you may have to optimize using one of several different criteria, or possibly a combination of them. You might have to compare several algorithms that are all correct. And how do you decide which one is best? well, you would have to judge them on these other criteria besides correctness. Correctness is usually the most important one. It doesn't matter if a program goes very fast if it doesn't give you the correct result. I mean, I can always make a program that's very fast if I don't have to give you the right result. So when you evaluate how fast the program runs, is your evaluation just done by taking a stopwatch? If you do that, the answer will certainly change when you buy a new computer, as you do every few years, because computers keep getting better and faster and so on. So you would want to have an analysis of the speed of a program that is independent of the particular computer you just bought. You want to have something that is more general and more timeless, and something where if you compare one algorithm against the other, and you say one is better, this relationship of which is better is preserved even if you move to a different computer, or even if the computer is run on your friend's computer. So the purpose of this course is to find general methods for answering these questions regardless of the specific computing problem that we address. In our next video, we'll start by attacking a very common problem in computing, which in fact we've already mentioned as a subproblem in some of the 3 puzzles that I mentioned today, namely sorting. You already know quite a bit about sorting, you've already done quite a bit of sorting, so let's see if there is anything in this topic that may still be a new and interesting challenge for you. See you next time.